Alright, so what we're going to do now is actually look at a reaction and start to bring some of this together. Because as we've said, a large number of the reactions that we're going to learn, the reactivity is based on the interaction of nucleophiles with electrophiles. And what we will normally see is the nucleophile is of course the one with higher electron density. The electrophile is the one that wants electrons. And so when we draw mechanisms, the arrow will go from the nucleophile to the electrophile. So let's look at an example. So this is actually one of the first reactions that we'll cover when we get to reactions of alkenes. It's the addition of a hydrogen halide to an alkene. So the first question is, what's the nucleophile and what is the electrophile? So we said previously that we know alkenes can be electrophiles. Now with HBr, this is a molecule where we have a polarized bond. The bond is polarized towards the bromine. And so the hydrogen partial plus, partial minus on bromine. So with the hydrogen having low electron density, it's a potential electrophile. The bromine has high electron density and could therefore be a nucleophile. So which one is going to be the nucleophile? Is it the alkene or is it the bromine? Well, in this case, we know it has to be the alkene. And the reason that we know that is actually fairly straightforward. If the bromine was going to be the nucleophile, well, it's already attached to the hydrogen, which is our only electrophile in this reaction. So it couldn't really react with the hydrogen because they're already bonded. So that leaves the alkene as the nucleophile. So the nucleophile attacks the electrophile. And so we're going to get a new bond formed between the carbon and the hydrogen. But we can't stop at this point. This is not the full mechanistic step. Why can't we stop here? Well, if we stopped here, we would now have the hydrogen, which is already bonded to the bromine, would also be bonded to the alkene. That would mean the hydrogen would have 2 bonds or 4 electrons. And that's more than hydrogen is able to have. Hydrogen, of course, being in the first row of the periodic table, can have at most 1 bond or 2 electrons. So what has to happen? Well, the hydrogen would also have to break a bond. And this is very, very common in mechanisms. If an atom already has an octet and it forms a new bond, it's going to have to break a bond. Sometimes that means we have to choose, but here the only other bond that the hydrogen has is the one to the bromine. And so that hydrogen-bromine bond breaks with those electrons going to the bromine. We will eventually use the term leaving group for what the bromine is doing here because it's the group that's leaving. All right, so here's what was our alkene. It's no longer an alkene. And the reason for that is these electrons, that were the pi electrons, they are what did the nucleophilic attack to pick up the hydrogen. But in addition to that, what that means is that the other carbon of the alkene, this one over here, is now missing electrons. And so it becomes a carbocation. The bromine that ended up leaving from the HBr has extra electrons, and it's going to be negatively charged. So this carbocation here is not the final product. This is an intermediate. But because it's positively charged, it's also going to be a good electrophile, whereas this negatively charged bromine is a good nucleophile, and we can get an attack to occur here, which now forms a new bond between carbon and bromine and gives us our product. So an intermediate, just in case you've forgotten that definition, intermediates are a very short-lived species that are found in the middle of a reaction. And specifically of a reaction mechanism. The other thing we know about intermediates is, again, short-lived. High energy. And not terribly stable. All right, so let's look at a couple more examples and then you have some practice to try. All right, so in this example, what's our nucleophile? What's our electrophile? Well, in many cases, if you find that something is negatively charged, if something is negatively charged, it's almost always going to be a nucleophile. A species that's negatively charged has electron density to give up. And just like in the last example, this hydrogen-chlorine bond is polarized towards the chlorine. So the hydrogen we know is a good electrophile. And we can draw an arrow from our nucleophile attacking our electrophile, which results in breaking the hydrogen-chlorine bond. Here's another example. Carbon double bond to oxygen, or carbonyl. Carbonyls are highly polarized towards the oxygen. That means our carbon of the carbonyl is almost always an excellent electrophile. H- being negatively charged has high electron density, makes her a good nucleophile. And so our nucleophile here, H-, attacks the carbon of the carbonyl. Now, just like with the hydrogens we've seen in the last two examples, this carbonyl already has the correct number of bonds for carbon. And so if this nucleophile is going to attack the carbonyl, we need something to sort of offset that. That carbon has to give bonds or electrons up. Now, two of the bonds it has are in this case, are to methyl groups. And so if one of those bonds breaks, it's going to take the electrons with it, and we're left with a methyl anion, which probably doesn't sound very stable, and isn't. But the other bond is a bond to a highly electronegative oxygen atom. And so we can take some of these pi electrons and push them up onto oxygen. And so this would form this intermediate, which could then go on to react further. So at this point, there's actually two in-class exercises, 17 and 18. And and you should work on those, and then we'll go over them in a little bit, and then after that we just have a few things to finish up in this chapter.